All right. Hey, Will, how's it going? I don't believe
Hello.
you've joined before, have you?
Yeah, thanks for the inviting.
Okay.
It's about the low calculus group studying. Yeah.
Yep. Yeah. So we're doing a right now. We're sort of following along with Greg's class, Introduction to the Design of Computational Calculi. I don't know if you've seen those YouTube videos uploaded, and so we're sort of using this group to discuss that class, and it's open to anyone to join. And then we're also just sort of like, yeah, helping. I'm here to answer like any questions, and the other people who are in the class are here to answer any questions that you might have about that class, and then we're here to like do the exercises together and stuff as well.
Okay, okay.
Yep. Cool.
I have a question about the lesson two.
Yeah.
I don't really understand about the free name and the binder. What do they mean?
Sure. Yeah. So we can talk about that a little bit. Let me da, 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 da. Let me share my screen here. Let's see. Let's share. All right. So say we have any sort of program that we can think of. Let's just sort of I don't know. Let's just go with a PyCalc program for now. So say we have the program xy dot p. So what this means is that we are going to look for something coming in on channel X, and then we are going to say that y is going to be a variable that is going to take the value that is anything that of the thing that came in on channel X, and then in the process P, so say the process P, actually let's expand that further. So say process P was going to take on the channel Y, it was going to send out the name Z. And let's just make that like, actually maybe we should do this in Rolang instead of PyCalculus. So that would be for y from x, and then we're going to send out on y the process 0, which is or let's just say the process P. Okay, so yeah, here we have that's yep, we're receiving something from X, binding it to Y, and then in this process over here, we're sending out on that name Y the process P. So we realize that this name Y, there's nothing special about it. These two processes, they do the exact same thing.
Yes.
You can see that, right? Yep. So what that means is that we have taken something. So in this process here, so these two processes though, and these are not the same, right? Because this right here, Y is a free name and Z is a free name. So right, if they are the same, then it shouldn't matter if we prefix the same thing in front of them, right? So we just prefixed an input to this, and we prefix the same input to this. If these two processes here were equivalent, then we would expect that the overall top level process is equivalent. But that's not the case, right? Because here we're receiving from X binding on Y, and then we're sending on some other name Z that we don't know.
Yes.
Right. So that's what the definition of free name and bound name is getting at, is this idea that these top two processes are equivalent because the name y is bound here. And so that sort of like erases the, it erases the variable name y. Whereas down here, you know, z is free. So these processes are different, right? We still have this name hanging out there. Does that help?
Yes.
Cool.
Okay.
So then, did you want to go back over the free name and bound name definitions of the row calculus and see that, or do you think that all makes sense now?
I have to think about it for a while. Okay.
Okay. All right. Sounds good. Yeah. Let me know if there's any other questions. Does anyone else? Cool. Does anyone else have any questions on anything from the first 3 sessions of the Introduction to Design of Computational Calculi? Or things that they'd like to discuss? I know I'd like to discuss both the Scala homework that we have for this week, just because I think it's quite a bit more challenging than the previous homeworks that we've had. And then I'd also like to just talk a little bit more about KFramework and the doing the structural equivalences for the pi calculus in KFramework. I've made some headway on there. I'm still not completely done with it. It's a pretty challenging task, but yeah, we could look at some of that together too. Also, if anyone has done any of the exercises or started any of the exercises and wants feedback on it and wants us to talk about them, I'd be happy to do that too. I'd be happy to start there. Also, I guess, sorry, yeah, Will, would you like to introduce yourself since this is the first time that you're here?
I'm sorry. I'm from China. My name is Will. Hello, everyone. And I'm a Python and Golang developers. Nice to meet you guys. Yeah.
Nice to meet you as well. Hey, Will.
I'm watching the videos about the Grab talking about the row calculus. Yes, and
Cool.
then I joined this study group. I hope we can work out something here. Yes.
Yeah,
Thank
awesome.
you.
Yeah, glad to have you.
Will. Hello.
All right. So let's hey. So cool. Let's just jump in. Does anyone have a preference looking at Scala code or KFramework code first?
I vote for KFramework, but I'm happy either way.
Okay, cool. Let's go into KFramework stuff. All right.
Hey, Jake, just FYI, I'm seeing a lot of flickering in the terminal. I don't know, is anyone else getting that?
Oh, are you?
I don't get any flickering. Oh, I just got one.
Yeah, me too.
Okay. Let me try to just do the whole desktop share and see if that gets any better. Thanks for letting me know. How's that? Better, worse?
Yeah, so far better. Maybe, not worse. Definitely not worse.
Okay. All right. We'll just keep it here then. I think Zoom and my Linux installation don't play very nicely together, unfortunately. Anyway,
Yeah, you should deinstall that Ubuntu and install SUSE.
And install what?
OpenSUSE.
Yeah?
Yeah, it's really cool.
Okay. I'll give that a shot. Yeah, right now I'm on a weird exotic Linux installation. I'm using Gallium OS on my Chrome device, and then I have Docker containers that are Debian that I do all my dev out of. So maybe I should just try to go with the straight up Ubuntu.
Yeah, I'm sorry. I know I'm digressing here, but it's the oldest Linux installation. It's been installed on mainframes. It's really robust. I've been with them since the late 90s.
With Ubuntu?
No, OpenSUSE.
OpenSUSE. Okay. Yeah. Cool. Yeah, I should give that a shot. All right. Oh, actually, yeah, another exciting thing before we get into the PyCalculus. Remember last week, Joshi, when we were talking about if you had like a div and a mul, and you wanted to tell this to read left from right?
Yes, I do.
Yeah, so I figured out that you can use this syntax left, and then if you have like the K labels up here for each of these, and you throw them in there, then that will remove your parse ambiguities, and will read the groupings of muls and divs from left to right. And I can demonstrate that. So
with equal priority, or yeah, good.
Yeah, right. So let's demonstrate that. Let's comment out that line. Let's compile. Give it a couple seconds. And then here's an example. So 1 times 2 divided by 3, we're expecting this to have some parse ambiguities in our current definition. So let's see if that's the case. So we will cast negative, give us all the warnings. And we see that we do indeed have a parse ambiguity between the mul and the divide. So now we have this syntax. Okay. Compile that. And then do the same thing. Try to cast that. And we see that the parse ambiguities have been removed, and we see that the multiplication is taken before the division, which is exactly what we wanted. So that answers that question.
Sorry, I was muted there. Can we do a quick example with the opposite order, where it's
oh, yeah.
the division?
Yep.
Yeah, nice.
Oh. Yep, so the division happened first.
Yeah, oh, yeah. Oh, yeah, right. Very nice. Very cool.
Yep. All right. Cool. So now let's look at the PyCalc stuff. I have the syntax all defined here. We've gone over sort of how to define the syntax, but does anyone who's either yeah, I'm wondering if I should go through this again for people who haven't seen it, or if there's any questions here about defining the unambiguous syntax. If no one speaks up, I'll just move on.
I think a quick review would even help me, even though I've kind of followed along with some of it.
Okay, cool. Yeah?
Jake, can you hear me?
Yes, I can.
Okay. I know I'm a little late, but
Ooh, you're breaking up quite a bit. Do you maybe want to type your question or comment in the chat? I can look at it there.
part of the class when it started, or All right, okay.
Okay, are we working on computational calculus or rolling? Okay, so this is, what this is this is a, so rolling, I guess, kind of stems from computational calculus. What we're working in right now is a language called KFramework, and we're using KFramework to define the pi process calculus. That's our goal right now. So right now they're in the Rolang repo. They are also trying to do something similar by defining Rolang, the syntax and semantics of Rolang in KFramework. So I'm just trying to get us to start with a smaller language, which is actually still fairly complex, but so that we can hopefully understand, you know, some of the large KFramework definition of the row calculus. That's my goal, and I think it drives a lot better understanding of what's actually going on behind the scenes of the pi calculus when we can understand this KFramework definition. I've learned a lot from going through this. So the first thing that we're doing up here is defining the syntax of pi calculus. So we can look at, actually, let me just pull up the syntax. I really should just save this PDF. I always just Google it and go to this link. So the syntax of pi calculus, right? We have these different generators. So we can just sort of see these generators right here. So we need to import some notion of names into pi calculus. That's necessary for us to continue to get anywhere. And for names, I'm just using this KFramework predefined module ID, which just allows us to define sort of common variable names. So that means X or Y or hello or you know, different strings that you could think of as variable names in a bunch of different languages. They'll be allowed to be our names in the pi calculus, in this pi calculus definition. So we also have a syntactical element for process, and I'm saying that we can either have a normal process, which is this up here, and I'm saying this thing looks really complicated, so I'm just going to define that later down in my code. Or it's a process in parallel with another process, or it's this this replicated process, or there's new X and P, and so instead of using the symbol V here, I just used the word NU. And then I've added one thing, which is parentheses, which is just sort of a process grouping, just allows us to sort of give precedence. It's not necessary, but it makes things kind of nice. And then I also gave it, KFramework allows you to, if you just have something that's sort of a bracket and give it that label, then that means that it doesn't actually create a new node for it in the abstract syntax tree. It just sort of is saying that all this is really a bracket around a piece of our code. Yeah.
So is go ahead.
The characters NU would also be a valid ID.
Yeah, that's true. So we'll get parse errors if we try to use NU as a variable name.
So it just that's a KFramework. Oh yeah, it won't parse it. How does KFramework just choose to take it as a keyword versus an ID? Do you know?
I don't know. No. Yeah, that's a good question. Yeah, if you figure that out, let me know.
Okay.
Because yeah, it feels like there should be a better way to do this.
Well, I think normally the Lexer would do that, and it would have a priority, but okay, interesting. Okay,
Yeah.
thanks.
So when you put bracket there, at first I didn't have bracket there and I didn't notice any problems or ambiguities. Is it an optimization thing or how does that work?
Yeah, no, there won't be any problems per se. It's just sort of yeah, it's an optimization. It can sort of reduce the output of your abstract syntax tree. It's not necessarily
Okay.
yeah. So it's a little bit of like data compression on your parse program.
Okay, got it. And then what if so like you've chosen a pretty normal like pair of symbols to be varied as brackets there. Like what if we do something super weird? Like instead of left paren and right paren, what if we do like left paren and right square bracket or just like letters or something?
Yeah, I think you can totally do that.
Oh, okay. Okay, cool.
Yep. And then the other thing that we have here is because we don't want our grammar to be ambiguous, we've defined for process constructions that sort of have a process on either side here. And so say we have 3 of these in a row, we don't know if we take the biggest grouping on the left and the smallest grouping on the right, or the smallest grouping on the left and the biggest grouping on the right. We define that it's left associative here. And then,
so
yeah,
this is parallel process, yeah?
Yep, this is parallel processes. Yep, so I've labeled them par. Yep, so these K labels are, yeah?
Go ahead. No, go ahead. Keep going.
So yeah, these K labels are just essentially names that we can give to these grammar constructions so that we can reference them later on in our file.
So my question was about left in that line that your cursor's on.
Yep.
In the expression example that you just showed, you did left a different way. I forget exactly what the syntax was, but it was maybe like on its own separate line later. So is this just a shorthand for when you are only applying it to like this one par operation as opposed to like a group of them?
Yep, exactly. And actually you'll see here, and I don't know if this is necessary or not, I haven't tested it, but I did actually have the lefts here too, to say that multiply is left associative, divide is left associative, and like multiply and divide are on the same order of precedence and left associative.
Okay, got it. Yeah, so I'll do that afterwards then. If you're saying like you don't know whether getting rid of the individual one that you're looking at now and the one right below it will make a difference, right?
Yeah, I'm not sure.
Okay.
I think it yeah, I don't know. It might make a difference if you have like a times 3 things in a row, but it might not. I haven't tested that.
Yeah,
so
that's a good thing.
But yeah, if you test that and let me know, that would be awesome.
Yeah.
Okay. Then I've said that we have this syntactical element for normal processes, which takes some sort of pi input prefix, which I've left below. And then there's a process. Nilk is a normal process, and you can add 2 normal processes together, and I've given that the K label or. And then there's the 2 different, this is my receive here, if it's the normal parentheses. And then if I have the angle brackets here, I'm saying it's a send. So that's my PyCalculus syntax, because it's hard to put a bar like in the PyCalculus paper here. That there's, the send atomic action has this bar over the name that's being sent on, and that's hard to do. So I've just surrounded the Y with angle brackets instead. Okay, and then there's this priority. So this helps me remove all the ambiguities. I want to say that the things that are tightest bound are my replication, my new, and my prefix. And then the next sort of level is my ors, so all the things that are added together. And then at the top level, the whole par is sort of the weakest binding element in the grammar. Yeah. What questions do you have about the grammar definition?
You said about 2 normal processes. Can we apply more like asynchronous process, like they never stop or something like that?
sorry. So can we have create different elements, different types of processes?
Yeah, different types of processes, and they never stop. Like they're going and going and making each other, you know.
Sure. So so in the pi calculus, we don't have any construction that's like that, and maybe the replication is sort of like that, which says that if we put a bang and then the process p, that's kind of like an infinite numbers of p's running in parallel. But yeah, we're not right now. You could certainly extend the pi calculus here, but we're just trying to put in just the pi calculus into this definition.
Okay, okay. So it doesn't have some range. Okay, thanks.
Yep. Okay, so once we've defined our grammar, now we want to sort of define our structural equivalences. So here's where we get into sort of the meat of KFramework a little bit. So the first thing, don't get scared by this huge, large sort of XML-like looking thing, but we have this XML-like tree which defines our program, and it's called a configuration in KFramework. So the whole configuration is sort of inside of this T element, which I'm just calling like T for top level process. This is a KFramework convention. Now inside of my top level process, I say I have one par, which, you know, this is the top level par that we talk about. You know, at the top level, all a rolling processes is a whole bunch of processes running in parallel. So I guess par and top, I probably could have combined those together, but whatever. And then I'm saying that each, in that top level par process, we have a whole bunch of these different procs or processes. And so we're saying that it has a multiplicity of star, meaning that there is 0 or many of these. And then inside of our process, we have a K cell. And a K cell is a special sort of cell in KFramework. It's sort of what contains initially the syntactic elements that we've defined. And it sort of defines a running process. So a running process is sort of exists inside of a K cell. And then there's a whole bunch of other stuff that I've defined below that that is also inside of this process element. But we'll get to that later. The important piece to know right now is that initially what happens is our whole program component. So $program is a special term here. What the $program is when we call krun, the term that is returned from krun is going to be put into the place where this program variable is. And since our syntax defines many different syntactical elements, name, process, normal process, pi, I'm saying that I want you to place in there an element of the type process. That is what a valid program is an element of our type process. And I'm just going to have you put it initially inside of this single K cell, inside of this single process, inside of this single par, inside of this single top level configuration. What questions do you have about a configuration and so far?
I don't know if I have a fully formed question yet. I see that you're sort of nesting a par. So like a par comes first because in PyCalc, we can have lots of things running in parallel at once, and that's okay. And those things inside a par can be 0 or more processes, right? I guess my question is, aren't those things redundant with just having your top level thing be a process, because your syntax already defined those rules?
Yeah. So I guess that'll start making sense when we get into the rules explanations a little bit, I think.
Okay. Yeah, I'm happy to hold up.
Yeah, let's go with that. Let's look at our first structural equivalence. So our first structural equivalence is that P and par and 0 form a symmetric associative monoid. So what that means is that you know, P par 0 is equivalent to P, and P par Q par R is equivalent to P par Q par R. Okay, so that's the first thing that we're looking to define. So the way that we're going to do that is by these rules that we've tagged as structural. Because it's a structural equivalence, it's not a reduction rule, it's not actually symbolizing a step of computation. And so now what my goal is that any sort of structural equivalent process is going to look the same when we call krun and we don't have any reduction rules defined. So let's actually do. So remember we had this 1 divided by 2 times 3, and then in EX, well, yeah, let's actually do, so let's define in our expression language, we have a configure, let's just make sure I'm getting all the syntax right. All right. So let's say we have a configuration which has a top level element, and then we have our K, which has our program in it, and we won't give it a type because I think yeah, I guess we can give it our type because our top level type we want to be an expression. We go to type exp. So we'll compile that, and then we'll run ex1.exp and see what's returned. So see, we have our whole term inside of a K cell inside of this top level configuration, and there were no rules for how to reduce that afterwards. So that's what we have. That's our sort of bottom element. That's what's getting returned to us by krun. All right. So yeah, that's a similar sort here. All right, so now when we're talking about our rules, we want these rules to be, I'll just explain what the first one does. So the first rule that I have is saying that, okay, say we have a K cell that conforms to this form, which is some arbitrary P of type process in parallel with some arbitrary Q of type process. What I want to do is I want to reduce this K cell to only contain P, and then I want to, down here, saying this dot bag and then this arrow means that from nothing, I'm going to create a new process that contains K, another K cell with Q in it. So now we're saying that, you know, if in a top level par context, right, we have this K cell which has two things running in parallel, that's really the same as having like two separate K cells with each component, you know, each reducing in their own way, right? There's nothing special about having those two right next to each other. We're splitting them up. We're putting them into this bag, or to this like whole soup of things that are processes that don't have any necessarily list ordering to them. And then we're saying that if we have a K cell which is just the process nil, that's nothing. So that whole process here, this whole process that contains a K cell with nil in it, will get reduced to nothing, dot, the bag element. So now what we can do is, if we have, so let's see, our ex1.py. So if we have nil in parallel with nil in parallel with nil, that should look the same as if we krun just nil, right? Or I guess put another way, let's just do this. So this should look the same after we krun it as just this, as if we had a file which was just this element. So let's give this thing a krun and see what pops out.
You know, right here, as an aside, all these nils is a common issue sometimes when you deal with data flow. You have all these stop processes floating around in the namespace.
Yeah. Oh, right, because yeah, so this is actually removing all the stop processes. That's what the definition is doing. Killing them. Or it's saying that no process at all is equivalent to having your stopped process running in the same context. So here we see really like the only element that we have is this. There's a whole bunch of different rules that I've defined too. I probably should have started with a smaller definition, but really all we can see is this xy.nil. We don't have any nils running around. So let's just to prove to you that this is the same, I'll just do that, and we can krun it again, and we should get something that looks exactly the same. Yeah, so same thing. No nils floating around. And then also, right, this, yeah, let's just move on to the next. Yeah. Yeah, and KFramework doesn't really care about when you have, let's just run that again. Yeah, KFramework doesn't, when we're saying that we have inside of like one tag, we have a whole bunch of different tags of a certain multiplicity, it doesn't really care about the ordering of those tags, which we will see later. So, right, this proc, just because it's printed after this proc, it doesn't really actually matter to KFramework which one's first and which one's second. It knows that this is an unordered set.
What are the K cells with dots in them there that were just in your output?
Yeah, so this means that there's nothing in there, which I'll continue showing you my rules, and then maybe that'll make sense. So now we have this rule for the structural equivalences of the par and element are pretty much satisfied. So now we want to also do a rule for the sum element. Now, this is a little bit different because when we have this sum element, we can think of, when we have a normal process, we can think of it as nothing is really running. We have just a bunch of things that are waiting to run. They're either waiting for an input or waiting for an output to happen. And n plus m. So if I have something waiting for an input and something, if I have two things waiting for an input from two different names, and I've added those together, that's different than if I have two processes running in parallel, which are waiting on each of those same names. Because remember that what a sum and means is that once one of those communications happen, only one communication in a sum can happen, and then the rest are evaporated once that one communication happens. So we can't just pop these all out, this normal process out into a whole bunch of separate different processes like we did before. I'm saying what we're doing is we're going to take, when we've reached the form, when we've reduced our term to the form such that there's only one normal process inside of a k-cell, we're going to call that k-cell stopped. So we're going to say that there's nothing inside of it by just reducing it to period, which is sort of our empty type. And then what we're going to do is inside of the k-cell, we are going to put n, that normal process, into a summand hole. So here's a term that we have here. I have a sum term which has 0 or many summand terms and is initially empty when we create a process. So now I'm filling it with n. So I'm saying once we've reached the form of a normal process, we throw it into a summand, and then we're done. Oh, this should be structural too. Then I'm saying that if we have a summand that is actually two things added together, we can break that up into, just like we had our par up there break into two different cells, we're going to have this break into two different cells too. So something of the form n plus n inside of a summand is going to reduce to an n, and then we're going to create a new summand term which is going to exist inside of the same sum, which is an m. And then now we need to say same thing. If we have a summand that's a nil, it's going to get removed from our sum. And then we need one final rule down here, which is going to say that if our sum is empty, we have the dot. And if our k-cell is empty, we have a dot. Then that whole thing is going to be empty. So you'll notice now that these dots have different types associated with them. There is the list type. So actually, I think this is equivalent to calling to dot list. So there's lists and bags, which are lists and sets. K-cells require lists because the way that they're configured, and we're not really using this property of them in our pi calculus definition, at least yet, is that, like, say you had a traditional imperative language, what a k-cell is a whole bunch of different, like, do A, then do B, then do C, like reductions that are put out in a row together to let you know that's sort of how k-cells are usually configured, but we're not really using that property of them here. And then we need to specify for some reason that these are bags. Otherwise, the compiler complains. All right, what questions do you have there? Maybe we should look at some examples. So here's an example. We have two processes here, or three processes from the par level here. This first one, this second one, and this third one. And really what we're saying is that since we're talking about structural equivalence here, really we should be erasing this last term, nil plus nil, because that's not doing anything. And we should be erasing this nil here that's in our addition. And really the only information that we should see is this x listening on x, and this other listening on x binding to both y and z. Those are the two things that we should see when we k-run. So, yep, we see that we have two processes, one process there, and one has in the summand listening on x, binding at y, and then this process nil following, and the other one has listening on x and z, and then this nil process following. So once we implement our reduction rules, I'm planning on, taking our reduction rules and saying that, if we find an input and output matching, then these K cells, which are empty up here, are now going to be filled with whatever came after the input or the output action. That's what I'm hoping to do. Then I started doing some of the bound name properties. So we have this property where new x binding any name in the process 0 is just equivalent to the process 0. And binding one name, then binding a second name in the process P is equivalent to binding the second name and then the first name in process P. Those are the same. So our bindings they can be unordered here. So the way that I'm doing that is I'm defining this new bag called bounds, right? Because bags are where we store unordered things. And that you can see that each process has a bag here of bound names, and each bound name will have its own bound cell. So I have, if we have something of the form new xp, we're just going to reduce it to p in that K cell, and then we are going to put in the bounds the x, whatever x was. Now, there is a problem here. This rule is not complete yet. Does anyone know why? Or yeah, there's an issue here. I think.
I don't think it's the ordering, because a bag you said is like a set, right? So that's unordered.
Yep. So the issue is now, what if P is of the form P par Q? If P is of the form P par Q, then I don't know that X should be bound in both P and Q. But in our definition of par up here, when we split that out, we're not bringing our bounds with us. So we'll need to do that. So let's see, where's another ex3.py maybe? So new x, xy.nil. So let's just say this is new x, and then yeah, this is xy.nil in parallel with whatever, an input process of the same name. So x should be bound in both of these. Let's see if it is or not. And then we have this new y nil, which should just reduce to nil again. We can check that. I should just start scheduling these things for an hour. We pretty much always go an hour anyways. Okay, so, right, we see that this first one has x in the bounds, and the second one doesn't have x in the bounds. So we need to copy that over. I actually haven't done this yet, but let's see if we can just do that quick. That'd be kind of fun. So we have this rule process, and then let's say that so I think we need to put this inside of a proc. And then we have our bounds B, we'll just call them so these dot dot dots means that there can be things before and after this. And now in this case cell here, we want bounds B bounds. So we should want to copy that all over. Let's see if this works. I hope it does. For some reason, in my installation of KFramework and the Docker installation too, for whatever reason, these rules aren't compiling using the normal backend. So I have to specify backend Java to get these things to work. I don't know why that is. I think it's a bug, but I haven't talked to anyone about it yet.
How did you figure out that the Java backend worked? Just trying?
Yeah, just testing. Fingers crossed. I usually test my examples before class. Hey, now we've copied over the bounds to bound variables as well. Awesome. So happy that that worked. Thanks for the clapping, Joshi. Okay. Yeah, so I'd encourage you guys to dig into this a little bit. I can upload this and you can look at it, but there's still a lot left to do. There's still the replication operator, and there's some interesting things there. I think in the PyCalculus paper, actually, there are some structural equivalences which aren't explicitly stated but are implied, and like don't have any formal reasoning. For example, ooh, there's some chat here. I don't think. Oh, paste the link of the PDF. Yeah, this is the PyCalc PDF. Is this an issue number? So what is 7437? All right. Anyways,
no, somebody asked me about my name in Discord, and I posted it. That's it.
Oh, okay. Okay, cool. All right, so for example, it's not really defined in here that what happens if we have not P. I don't think our structural equivalences tell us, like, I don't see any way that that's not equivalent to not P, to just bang P. But yeah, there's nothing in here that tells us that explicitly. It also, another difficult thing that's going to happen is that in this form of the PyCalculus that's talked about in the paper, what we'll want to do is also specify that if we have like this, should be structurally equivalent to just bang nil, right? So we have two nils in parallel. So structurally equivalent things that are replicated should be structurally equivalent. But in this version of the pi calculus, at least presented in the paper, reductions can't happen under replication. So that means that we're going to have to define a new type of cell, which we sort of port everything into. We need to redefine all of these structural equivalences for things that happen inside of a replication, but then also make it so that reductions don't happen inside of there. I haven't thought of a really elegant way to do that without repeating myself a lot in KFramework, but if anyone has any suggestions, I'm open to them. I think what I might end up doing is like making a tag element for replicated processes and putting that tag into the configuration, and then checking to make sure that that tag isn't there whenever I'm doing a reduction, but allowing the structural equivalences to happen.
Why did the paper say in the first place that reductions can't happen under replication?
So second, the rules do not allow reduction beneath replication. In some cases, this does not reduce the computational power.
After you replicate, each one can still reduce, right?
Right. So like the replication itself doesn't reduce, but the replication is equivalent to the replication with a process spawned in parallel with it, and that process can reduce. So
if that's how you implement replication, then it might just be, but you got to make sure it doesn't reduce first before things get replicated, right?
Exactly. Yeah. So it's gonna get a little tricky there, but it'll be fun. And there are also some things that. What else do we need to do for structural equivalences? I think that actually might. Is that close to it? Once we have the bound. Whoa. Oh, we need to import the alpha equivalence too. So yeah, we need to import the alpha equivalence. So we need to somehow say that if we have two processes that are the same except for their bound names differ, that those are structurally equivalent processes. That would be needed to complete our structural equivalence as well. So yeah, those are things that we could still define. Yeah, I guess the only other things that I have for this week that are kind of cool, I think that there's a pull request that's open right now for the Rev Blessed contract, which has a whole bunch of fun Rolang in it, and Rolang that looks like it's closer to what it actually might look like when it's deployed, with a whole bunch of like Scala tags in there too. So we have this like Scala package that's coming, that's like inside of a Rolang file. So that's kind of neat. I haven't looked at any of this yet, but I'm excited to look at that this week. And then also, in the introduction to the Design of Computational Calculi repo, I opened issues for the exercises, both the exercises that I have. So we're on Jake exercise 02 is pretty much what we've been working on right now, which is to find the structural equivalences of pi, calculus, and KFramework. So I'll post what I have there, and then hopefully other people can post what they have there as well, and we can discuss. I'll probably just like post a link to a gist here. And yeah, if anyone wants feedback on any of the assignments, the ones that Greg's been giving, or the ones that I have any post here, I will commit to responding to those. And yeah, if people who have done some of Greg's first exercises could go back and throw them in here too, that would be neat, just so that we could point Greg to one place where all the work's being done, because I know he's been missing those in emails that have been sent. So that's, I guess, where we should draw the line this week. I'll also upload what I have so far with the Scala implementation. I'm pretty excited about that, and I could probably talk for another 45 minutes to an hour about that. But yeah, any other comments or questions before we sign off here?
Jake, this is recorded. Where are the recordings posted?
The recordings are posted to my YouTube channel. You should be able to find, if you go to the let me find a link here.
Yeah, it'd be good to put it in the welcome, or
Yeah, so it is in the welcome. So in the welcome, I guess. Okay, I guess the YouTube playlist isn't directly there in the welcome. I can put it there in the welcome. But if you drill down into Introduction to Design of Computational Calculi, oh, yep, you're right. I guess you don't see it there either. So I need to get on my documentation a little bit. But if you drill down to the PyCalc to Rolling, where a lot of the stuff was happening before, you see the video indexes, which will link you to a Google playlist. And I'll just, since it's not really apparent, I'll get on that. But
okay, that's awesome.
I just put the link in the chat, and then also, I don't know if you noticed this, Jake, the individual links to videos are now updated to point to the playlist. So if you click on any one of those, it takes you to the playlist.
Awesome. Thank you so much for that, too.
Yeah.
And I usually get around to uploading them about midweek. It takes me a little bit. It takes me a couple days sometimes, but I'll try to do that quickly. Yeah, anything else? Cool. Nikita, I think this is your first time that you've been in this session, and David as well. Would you like to, ooh, looks good. Looking forward to incorporating K into ladle research, Christian. That's awesome. I am really excited to see where that goes. And I'd love to see any sort of work in progress on that. But yeah, Nikita or David, would you like to introduce yourself? Since I know this is your first time here, we'd like to learn more about who you are and why you're here.
Hello, my name is Nikita. GitHub name and Discord name is Kilentium. I'm from Greece, but I'm Russian, and I am starting to promoting RChain Collaborative in Russia. And I have studied Python a little bit for me, starting with JavaScript a little bit too. And now I'm looking forward to Roland. That's it.
Cool, awesome. What about David?
Yeah, my name is David. I'm a JavaScript and PHP developer, a member of RChain. So I think the whole Roland and RChain ideal is really cool. And I would like to collaborate, and I would like to contribute rather. I would like to contribute to the whole development. So I guess this class has proven to be useful over time. And I really want to, although today most of the things that were done I was looking lost, like I wasn't familiar with a lot of things, but I believe that with a little bit of time and a little bit of study, I should be able to catch up with everything that's been done. Yeah.
Sounds good. Yeah, awesome. Glad to have you. And there is, you're sort of jumping in the middle here. If you go back and look at some of our previous discussions, we've talked about KFramework more and what constructing a grammar means more. So yeah, I think it might be value to go even all the way back to the beginning of these discussions where we really talk about the pi calculus and what a grammar is and all of that in a fair amount of detail. So awesome.
So we can find it all on your YouTube channel, yeah, the previous discussions and etc.
Cool, great, awesome. And yeah, please come with any questions. And if you have questions in the middle of the week that you'd like to have addressed on the weekly discussion, if you could get at me during the week through email or through Discord, I'm totally open to that. So yeah, I want to help bring you guys up to speed. You shouldn't have to rely on just sort of going back and looking at everything that's been done. I want this to be inclusive. So yeah, thanks for coming. All right, with that, let's sign off. Thank you. Bye.